feeling of solid ground beneath your feet? We kind of take it for granted, right? But what if I told you that stability is, well, it's just an illusion? Deep down, there's this unseen machine, a hidden engine that's always working, building mountains, shifting entire continents. So in this explainer, we're going to peel back the layers and see this incredible, restless machine in action. I mean, think about it. It's the foundation for our homes, our cities, literally everything we build. But is it really solid? The answer is not really. The truth is, the continents themselves are adrift. They're moving across the planet in this incredibly slow but unbelievably powerful dance. So the big idea to wrap your head around is that our planet isn't static at all. It's actually a living, breathing system. Yeah, from where we stand, everything seems perfectly still. But deep inside, there's a fiery engine driving huge, relentless change all over the globe. Okay, so to really get how this engine works, we have to start from the inside and work our way out. So let's take a little journey right to the center of the Earth to see how the whole thing is put together. Probably the easiest way to picture our planet is, well, think of a giant egg. Seriously, we're living on the super thin, fragile shell. That's the crust. Underneath that, you've got the thick egg white, which is the mantle. And right in the middle, you have the dense yolk. That's the Earth's core. And when you look at the numbers, it's just mind-blowing. The crust we live on, our entire world, it's less than 1% of the planet's mass. It's practically nothing. The real heavyweights are the mantle, making up a staggering 84% of the Earth's volume, and about 2/3 of its mass, and that super dense iron-nickel core. So that begs the question, right? Where does all the energy for this movement actually come from? The answer is buried deep inside that massive mantle. It's time we meet the planet's fiery engine. All right, the key player here is this layer in the upper mantle called the asthenosphere. Now, this stuff is weird. It's not really solid, but it's not liquid either. The best way to imagine it is like a super hot, kind of plasticky layer that flows, but over millions of years. Think of super, super thick honey. And that slow churning movement, that's the source of all the power. The whole process is basically like a giant pot of soup simmering on the stove. You've got material deep down near the core that heats up, gets less dense, and starts to rise. Then, as it gets closer to the crust, it cools off, becomes denser, and sinks back down. This creates these huge, powerful circular currents. It's like a massive global conveyor belt. So this giant conveyor belt, what's it moving? Well, it's carrying the entire solid, rigid outer shell of the Earth. And here's the kicker. That shell isn't one solid piece. It's broken up into these massive plates. And that, right there, is the central idea behind the theory of plate tectonics. This rigid outer shell has a name, of course, the lithosphere. And it's not just the crust we're walking on. It also includes the very top solid bit of the mantle. The most important thing to remember is that it's not a single shell. It's shattered, broken into these huge slabs we call tectonic plates. So you can literally picture these massive plates. Some are carrying entire continents. Others have whole ocean floors on their backs. And they're like giant rafts, just floating on that churning asthenosphere. And that convection engine deep below is what's pushing and pulling these rafts all over the globe. And as you can probably guess, most of the real geologic action happens where these plates meet up. We're going to talk about a few, but the two main types are divergent boundaries, where plates are pulling away from each other, and convergent boundaries, where they're smashing right into one another. Let's start with divergent boundaries. This is where the Earth is literally making new land. As two plates pull apart, magma from the mantle rushes up to fill the gap, then it cools and hardens into new crust. A perfect real-world example of this is the Red Sea. It's actually a brand new ocean being born as the African and Arabian plates slowly drift away from each other. Okay, now for convergent boundaries. This is where the real drama is. When two plates carrying continents collide, that immense force has nowhere to go but up. So the crust buckles and folds, creating these absolutely massive mountain ranges. The Himalayas? Yup, the tallest mountains on Earth were formed exactly this way. And believe it or not, they're still growing, as the Indian plate keeps ramming into the Eurasian plate. Then there's a third type we gotta talk about, a transform boundary. Here, the plates aren't colliding or pulling apart. Instead, they're grinding horizontally past each other. The scary part is they often get stuck. The pressure builds and builds, sometimes for decades, until, bam, they suddenly slip, releasing all that pent-up energy in a massive earthquake. The San Andreas Fault in California? That's the most famous example of this. But you know, the effects of all this movement aren't just about big, dramatic events like earthquakes and volcanoes. This restless lithosphere, it doesn't operate in a vacuum. Its constant motion, its chemical makeup, it's all deeply connected to everything else on our planet, the air, the water, and even life itself. And this really shows it perfectly. You've got the lithosphere right there in the middle, and it's fundamentally connected to the atmosphere. That's our air, the hydrosphere, which is all the water, and the biosphere, which is, all living things. So let's break down how these connections work. So check this out. Believe it or not, rocks play a huge role in controlling our climate. It works like this. Rain falls and absorbs CO2 from the air, which makes it a tiny bit acidic. This weak acid then hits the rocks and slowly dissolves them. This whole chemical process actually pulls CO2 out of the atmosphere and locks it away in minerals. Over millions of years, it acts like a giant thermostat for the planet. And what about water? Well, the lithosphere shapes that too. As rivers and streams flow over the land, they're constantly dissolving minerals like calcium and magnesium straight from the rocks. This is what gives water its unique chemical makeup. It's the whole reason you hear about some places having hard water and others having soft water. It all comes down to the rocks. And maybe the most important connection of all is to life itself, the biosphere. Where does soil come from? It's created from the slow, relentless breakdown of rock, and that soil is what holds all the essential nutrients, phosphorus, potassium, you name it, that form the very foundation of the entire food chain. It's pretty simple, really. No rocks, no soil. No soil, no life as we know it. So when you put it all together, all this constant creation and destruction and interaction, it isn't just chaos. It's all part of this incredible, self-regulating system. Our planet maintains its balance because of this constant change, not in spite of it. And I mean, this process is just incredibly slow. Take the Red Sea again. It's widening by about 2.5 centimeters a year. To put that in perspective for you, that's roughly the same speed your fingernails grow. It seems like nothing, right? But you let that happen for millions of years, and that tiny little movement is enough to create a whole new ocean. And that brings us to this quote, which just nails the whole idea. The Earth's stability is not one of stillness, but of constant dynamic change. It is a system in perpetual balance. Our planet isn't stable because it's sitting still. It's stable because it's always moving, always adjusting, always finding its equilibrium. So that really leaves us with a pretty mind-bending final thought. The world map you see today, that's just a snapshot in time, a single frame in a movie that's billions of years long. The very same forces that ripped continents apart and built the Himalayas are still at it right now, silently shaping the world of tomorrow. It kind of makes you wonder, doesn't it? What's this planet even going to look like in another 100 million years?